Hello, everyone. This is the last of our videos on derivatives and what they have to do with the shape of a graph. And in this video, we're going to be talking about the second derivative test. This is usually the go-to test that people would use if they want to test to see if a function has a local maximum or minimum. And it works really quick and nice if everything's nice and differentiable. So let's go check it out. All right, so here we have the second derivative test, a theorem which allows us to find local minimums and maximums of functions. It doesn't always find them, but it works pretty well in very many situations. All right, before we explore the details of the theorem here, let's look at an example. All right, so here we see the graph of a function, all right, and this function has a minimum here. So what are the features of the graph at its minimum? Well, at the minimum point, we see that the graph has a horizontal tangent line. That means its derivative is 0. Moreover, if we think about the concavity of this function, we see that the function's concave up. And so we see that if the function has derivative 0 and is concave up, that corresponds to a local minimum. All right, let's take a look at another function. This function has a maximum here, right? Now, what's true at this maximum? Well, the tangent line is horizontal, and therefore the derivative is 0 here. And if you look at the concavity, we see that it is concave down. So if you have derivative 0 and the graph is concave down, we have a local maximum. Okay, let's look at this graph. In this graph, we have a point where the derivative is 0. It's right here. It has a horizontal tangent line right there, okay? So the derivative is 0, but it is neither concave up nor concave down at this point. To the right, it's concave up, and to the left, it's concave down. So we have negative concavity, and it changes to positive concavity. This is an inflection point. But the concavity at this, the second derivative at this point is 0. So it's neither concave up nor concave down. And you see that we have neither a minimum nor a maximum here. So concavity is integral to this process that we're using here. Not only do we need to investigate where the derivative is 0, but we also need to check to see if the concavity is positive or negative to confirm that there's a minimum or a maximum there. All right, so here we are back at the theorem. Let's read what it says. It says, suppose f prime of c is equal to 0, and f double prime, the second derivative, is continuous on an interval containing that number c. And the theorem has 3 parts. The first part says, if the second derivative at c is positive, then f has a local minimum at c. If the second derivative at c is negative, then f has a local maximum at c. And if the second derivative at c is 0, then the test is inconclusive. So let's just go back to those examples and just quickly verify again that those are correct. Here we have, at this point, the derivative is 0, and the second derivative is positive, and we do indeed have a local minimum. On this function, we have the derivative is 0, and the second derivative is negative, and we do indeed have a local maximum. And on this one, the derivative is 0 here, but the second derivative is also 0. And therefore, the test is inconclusive. Now, in this case, we don't have a minimum, nor do we have a maximum. The test doesn't tell us that. The test just says you need to use another test. Okay, so let's look at some examples here. We want to use the second derivative test to find the local maxima and minima of these functions. The same functions we've had in the last few videos. And in the last few videos, we've actually found the maxes and mins, but we did it a different way. All right? So let's go back to this function here and use this test. Now, to use the test, we're going to need to find the first derivative, right, and find where it's equal to 0. And then we're going to use the second derivative and check the sign of that to determine whether we have a local max or a local min. All right, so here's our first function, and we will first compute the first derivative, and we'll need the second derivative for this test as well. And these should, like I said, be familiar to you from the previous videos. And remember what the second derivative test says we need to do. We need to find where the first derivative is equal to 0. So we're going to set this function equal to 0. And we'll divide through by 3. And we'll factor. And we see the two solutions here. They are the numbers -1 and 3. Okay, so now that we found those are our values for this number c. We are now going to check the sign of f double prime and see if it's positive, negative, and hopefully it's not 0. Otherwise, we need to use a different test. All right, so we're going to plug these numbers into the second derivative. All right, so let's go ahead and do that. F double prime at -1. What is that? Well, if I plug this in here, I get -6 minus 6. It's -12. That is negative. And let's plug 3 in. F double prime of 3 is 18 minus 6. That's positive 12. And that is positive. And that's all the information we need. We now see that at -1, the second derivative is negative, and therefore the function has a local maximum at that number, at -1. And if we wanted to know what the value was at that number, you could plug -1 in to the function and compute it. And when you do that, you see you get 9 as the answer. And we can look at this next number over here. We see the second derivative is positive. And for that, the test says that there's a local minimum there. And the value is what we would get when we plug 3 into the function, and that would be -23. So very quickly, using the second derivative test, we can find where the local maxes and mins are and what their values are. And I think if you compare this to the video that we did with using the first derivative test, you'll agree that this is a lot quicker. They both work, but this one is, I mean, in my opinion, the preferred method. And let's just verify that what we saw matches the graph. We can see that we do indeed have a local max at -1, and the value of the function there is 9. And we do indeed have a local minimum at 3, and the value is -23. All right, let's do number 2. So we're dealing with this function. So we're going to find where the derivative is equal to 0 and where the second derivative is, well, at that number, we're going to check the second derivative and see if it's positive, negative, or hopefully not 0. All right, so we're going to have to compute the first and second derivatives. We've done that in the previous videos, so I just have got them already computed here. All right, and so like we said, we want to find where the first derivative is equal to 0. That can only happen where the numerator is equal to 0. So we're looking for solutions to this equation, and I think it's pretty clear what those are. X equals ±1. Okay, so now we're going to just evaluate the second derivative at these numbers. The second derivative at -1, we'll plug that number in here. What do we get? We get -2 times -2, so it's +4. Okay, you know what? I don't need to go and compute everything here. Looks like you're going to get 4 over 8. It looks like it's exactly 1/2. But you know what? I don't really care. I just need to know what the sign is, right? So it's a -2 times -2 is +4 divided by, I can see this is going to be positive because it's something squared plus 1 and cubed. So I don't even care what the actual number is. I can see that it's positive, and that's all that matters. And what about at 1? If I plug 1 in, I get 2 times -2 divided by something positive, and so the whole thing is negative. I don't really care what the actual value is. I just need to know the sign. And so we have a number where well, let's go to -1, where the first derivative is 0, and the second derivative is positive, and so that corresponds to a local minimum. And the value there would be what we get when we plug -1 into this, and that would be negative 1/2. All right, and then this one is that number 1 is a place where the first derivative is 0, and the second derivative is negative, and so that corresponds to a local maximum. And what would the value be? Well, I'll just plug 1 into the function, 1 over 2. That is positive 1/2. And let's just verify that the graph matches what we found. We see that we have a local minimum at negative 1, and the value of the function there is negative 1/2. And we have a local max at positive 1, and the value of the function there is positive 1/2. So it does match what we found. And for number 3, again, we need to compute the first and second derivatives to run this test. All right, so we've done these in previous videos. Here's the original function, its first derivative and its second derivative. We're looking for where the first derivative is 0, so we set this equal to 0 and solve for x. Add sine to both sides, divide both sides by cosine. Well, that's just the tangent. And so we're looking where tangent is equal to 1. And by the way, we're doing this on the interval 0 to 2 pi. So we're just looking for values of x in that interval. And as we saw in the last video, this happens when x equals, pi over 4 and 5 pi over 4. Right? So what we're going to do is we're going to check the values of the second derivative at these numbers. Okay, so the second derivative at pi over 4. So I got negative of root 2 over 2 minus root 2 over 2. That's negative root 2, and that is negative. At 5 pi over 4, sine is negative root 2 over 2. Cosine is negative root 2 over 2. So we have negative root 2 over 2. That's positive root 2 over 2. Minus negative root 2 over 2. That's positive root 2 over 2. That's plus root 2 over 2. So we have root 2 over 2 plus root 2 over 2. That's root 2. And that is positive. And so since the first derivative is 0 at pi over 4, but the second derivative is negative, it's bowl-shaped down, so we must have a local maximum. And what would the value there be? Well, I'd plug this into the function. And this is root 2 over 2 plus root 2 over 2. The value is root 2. And at 5 pi over 4, that the first derivative was 0 there, and the second derivative is positive, so the graph is shaped like this. It's concave up, and so it has a local minimum there. And what would the value be? Well, we just plug this number into the original function. Sine of 5 pi over 4 is negative root 2 over 2. Cosine is also negative root 2 over 2. And so when you add those together, you get negative root 2. And that solves the problem. And let's just check that it matches the graph. Let's see, we have a local max here at pi over 4. And the value is, that would be around root 2. And we have a local minimum over here at 5 pi over 4. And the height of the graph there is negative root 2. So it does match what we found. Now, I just want to throw in a couple more examples because I think they'll be useful to look at. I want to look at x cubed. All right, let's see where x cubed, what the second derivative test would say about this function. All right, so to run the second derivative test, we need to compute the first and second derivatives. Well, the first derivative is just 3x squared, and the second derivative is just 6x. Now, we're looking for where the first derivative is equal to 0, and I think you can see that that happens precisely when x is equal to 0. That's the solution. So we only have one value we need to check. We're going to evaluate the second derivative. We want to see the value of the second derivative at that value and check its sign. Is it positive, negative, or 0? All right, so let's go ahead and plug 0 into the second derivative, and let's see what we get. 6 times 0, it's equal to 0. Okay, so where are we on this chart? Well, we're in the third possibility. And so the test is inconclusive. Now, what does that mean? Does that mean that there is no local min or local max? Well, it doesn't imply that. There could be a local min or local max there. This is just saying that the test isn't giving us any information. So what would you do in this situation? Well, this is a situation where you could go back and use the first derivative test. The first derivative test would tell you the answer here. So you may ask, well, why didn't we just use the first derivative test to begin with? And the answer to that is that the first derivative test is a little bit more tedious. The second derivative test just runs so smoothly that it's very convenient to try to see if it works first. All right, and if it fails, yeah, go back and use the first derivative test. And if that one doesn't tell you anything, well, then you have to be even more clever. And by the way, here's a picture of what we were dealing with. We can see that the derivative is 0 at 0. That's what we found. And the second derivative is also equal to 0 there. And we actually, in this case, don't have a minimum, nor do we have a maximum here. So we can verify that by looking at the graph. However, the second derivative test did not give us enough information to make that secondary conclusion that there was no minimum nor maximum. And finally, one last example. I want to look at number 5, f of x equals x to the fourth. Okay, let's run the second derivative test on this and see what we find out. Okay, so we need to compute the first and second derivatives. All right, and we want to look to see where the first derivative is equal to 0. And we see the solution is only one value of x. It's x equals 0. And so we need to look at the value of the second derivative there. So I'm going to look at f double prime of 0. If I plug in 0, I get 0. And so the test is inconclusive. Now, what does that mean? Well, that means that we don't know. We don't know what's going on there. We need to use another test to see. Let's take a look at the graph and see what in fact is going on. Okay, so here we have the graph of x to the fourth. And you can see that we do have the first derivative is 0 at 0. And it does correspond to a local minimum. The second derivative test did not pick this up. If you use the first derivative test, it would have worked. The first derivative test actually would give you the correct answer. Second derivative test doesn't quite cut it. But again, the second derivative test is just so quick and easy to run that even though it doesn't always tell us the answer, it's worth checking. And remember, just because the test is inconclusive doesn't mean the second derivative test is giving us the wrong answer. It's just saying, you know, I don't know. You're going to have to try something else. But I think it would be a great exercise for you to go ahead and use the first derivative test on this function, x to the fourth, and verify that that is where you would find the minimum. Okay, so I hope you learned something. The value, the expediency, really, of the second derivative test. It's just so quick. When it works, you can just really quickly get the answer when it works. But we saw there were cases where it was inconclusive, and we'd have to go and appeal to another theorem. And the theorem that you would then go to probably is you'd try the first derivative test. That would be the next one to try and see if that one gives you the answer. But there are lots of other things you could try. Looking at the graph is a great way to see what's going on. You know, just being clever. Use your brain. All right. So anyway, that concludes the series of videos on derivatives and the shape of a function, of a function's graph. Like I said, I hope you learned something, and happy mathing.